Learning objectives. In this chapter, the user will learn the following in detail: edge detection, boundary detection, edge detection performance, boundary detection performance.
Introduction to image segmentation.
Image segmentation. It is the process of partitioning an image into a group of pixels which are homogeneous with respect to some criterion. Different groups must not intersect with each other, and adjacent groups must be heterogeneous. Result of segmentation is splitting of the image into connected areas. Classification of image segmentation techniques: local segmentation, global segmentation. Local segmentation deals with segmenting sub-images which are small windows of the whole images. Number of pixels available to local segmentation is much lower than the global segmentation. Global segmentation. It is concerned with segmenting the whole image. It deals mostly with segments consisting of a relatively large number of pixels. Image segmentation can be approached from three different philosophical perspectives: region approach, edge approach, boundary approach. Region growing. It is an approach to image segmentation in which neighboring pixels are examined and added to a region if no edges are detected. This process is iterated for each boundary region. If adjacent regions are found, region merging algorithm is used. It requires a seed to begin. Ideally, the seed would be a region, but it could be a single pixel as well. A segment is grown from the seed by assimilating as many neighboring pixels as possible that meet the homogeneous criterion. The resultant of segment is removed from process. A new seed is chosen from the remaining pixels. This continues until all pixels are allocated to the segment. The resulting segment fully depends on initial seed in which the neighboring pixels are examined. Algorithms vary depending on the criteria used to decide whether pixels should be included in the region or not. Connectivity type is used to determine the neighbor strategy used to visit the neighboring pixels. It offers several advantages over conventional segmentation techniques. The borders of regions found by region growing method are perfectly thin and connected. This algorithm is stable with respect to noise. Region splitting. It is a top-down approach method. It begins with the whole image and divides it up such that the segmentation parts are more homogeneous than whole. Splitting alone is insufficient for segmentation, and it limits the shape of the segment. Merging phase after splitting phase is always desirable, which is termed as splitting merging algorithm. Region splitting and merging. It is one of the segmentation techniques. It takes spatial information into consideration. Splitting and merging algorithm as follows. Let R represent the entire image, predicts P. Split or subdivide the images successfully into smaller and smaller quadrant regions. Quadrature tree. The splitting technique structure is called a quadrature tree. In the quadrature tree, root corresponds to an entire image and nodes correspond to subdivisions. The final partition is likely to contain adjacent regions with identical properties. The drawback may be fixed by merging and merging only adjacent regions whose combined pixels satisfy the predict P. Merging. Merge the adjacent regions that are similar. The procedure for split and merge algorithm is given below. Start with the whole image. If variance is too large, split the image into quadrants. Merge any adjacent regions that are similar. Repeat steps 2 and 3 iteratively until no splitting and merging occurs.
Example.
Apply split and merge technique to this image. Classification of edges. Points in an image where brightness changes abruptly are called edges. It is a significant local changes of intensity in an image. Edges are boundary between the segments. Edges are a very important portion of an image. Classification. Step edge, line edge, ramp edge, root edge. Step edge, perfect transition from one segment to another. Image intensity abruptly changes from one value to one side of the discontinuity to a different value on the opposite side. If segments are piecewise constant and pixels belong to one segment, then a simplicity model is implicitly used.
Line edge. If a segment of an image is very narrow, it necessarily has two edges in close proximity. This arrangement is called a line edge. Ramp edge. It allows smoother transition between segments. It is useful for modeling the blurred edges created from sampling a scene containing the objects not aligned to pixel grid. Roof edge. Two nearby ramp edges result in a line structure called roof edge. Roof edges are of two types: convex edges, concave edges. Boundary detection and its performance. Boundary detection. If a region border is not known, but regions have been defined in the image, borders can be uniquely detected. First, let us assume that the image with regions is either binary or that the regions have been labeled. Inner region border is subset of region and outer region border is not subset of region. Chain codes. Chain codes are used to represent a boundary. Uses a logically connected sequence of straight line segments. Line segments are used to represent length and direction. Direction scheme using 4 and 8 connectivity can be seen on the screen. Chain codes in digital image. Pixels form an equally spaced grid in X and Y direction. Chain coding can be created by following a boundary in some direction, say clockwise. Assigning a direction to the segments connecting every pair of pixels assumes a 1 pixel wide boundary. An example for chain codes using 4 connectivity can now be seen. Using chain codes, problems in chain code. It is sensitive to noise. Solution: resample using larger grid spacing. Normalize chain codes. Chain codes depends on orientation and different chain codes are used to solve this problem. Normalize chain codes. Chain code depends on the starting point. We can normalize the chain code to address this problem. Assume the chain is a circular sequence. Given a chain of 1 to n codes, n plus 1 equals 1. Redefine the starting point such that we can generate an integer of smallest magnitude. Different chain codes. The difference is obtained by simply counting counterclockwise the number of directions that separate two adjacent elements. And we can normalize different codes also. Using 4 connectivity. Difference. Count the number of separating directions in an anti-clockwise fashion. While difference coding helps, it does not make a chain code completely invariant to rotation. Image digitization and noise can cause problems. Nonetheless, it is a fairly common encoding scheme. Algorithm for inner boundary tracing. Search the image from top left until a pixel of a new region is found. This pixel P0 has a minimum column value of all pixels. Pixel P0 is a starting pixel of the border. Define a variable dir which stores the direction of the previous move along the border from the previous border element to the current border element. The representations for dir equals 0 and dir equals 7 are now shown. This figure shows the inner boundary tracing, direction notation 4 connectivity, 8 connectivity. Search the 3 by 3 neighborhood of current pixel in an anti-clockwise direction, beginning the neighborhood pixel. The figure shows the pixel neighborhood search sequence in 4 connectivity and 8 connectivity. The first pixel is found with the same value as the current pixel in a new boundary element. Pn update the direction value. If current boundary element Pn is equal to the second border element P1 and previous border element Pn-1 is equal to P0, the detected inner border is represented by pixels P0, Pn-2. The figure shows the boundary tracing in 8 connectivity. The above algorithm works for all regions larger than 1 pixel. Looking for the border of a single pixel region is a trivial problem. This algorithm is able to find region borders but does not find borders of region holes. To search for hole borders as well, the border must be traced starting in each region, or hole border element if this element has never been a member of any border previously traced. Note that if objects are of unit width, more conditions must be added. If the goal is to detect an outer region border, the given algorithm may still be used based on 4 connectivity. Note that some border elements may be repeated in the outer border up to 3 times. Outer border tracing. Trace the inner region boundary for connectivity until done. The outer boundary consisting of all non-region pixels that were tested during the search process. If some pixels were tested more than once, they were listed in the boundary outer list. The inner border is always part of the region, but the outer border is not like that. Therefore, if 2 regions are adjacent, they never have a common border, which causes difficulties in higher processing levels with region description, region merging, etc. The interpixel boundary extracted, for instance, from crack edges is common to adjacent borders. Nevertheless, its position cannot be specified in pixel coordinates. Boundary properties better than those of the outer borders may be found in extended borders. Single common border between adjacent regions. It may be specified using standard pixel coordinates. The boundary shape is exactly equal to the interpixel shape, but it is shifted 1/2 pixel down and 1/2 pixel right. The figure shows the boundary locations for inner, outer, and extended definitions. The extended boundary is defined using 8 neighborhoods. For example, P_4P denotes the pixel immediately to the left of pixel P. 4 kinds of inner boundary pixels of a region R are defined. If Q denotes pixels outside the region R, then let left R, right R, upper R, and lower R represent the corresponding subsets of R. The extended boundary EB is defined as a set of points P, P_0, P_6, P_7, satisfying the following conditions seen on the screen. The figure shows the extended boundary definition: A. Pixel coding scheme, B. Region R, C. Left R, D. Lower R, E. Extended boundary. The extended boundary can easily be constructed from the outer boundary. Using an intuitive definition of right, left, upper, and lower outer boundary points, the extended boundary may be obtained by shifting all the upper outer boundary points 1 pixel down and right, shifting all the left outer boundary points 1 pixel to the right, and shifting all the right outer boundary points 1 pixel down. The lower outer boundary point positions remain unchanged. The figure shows the constructing of extended boundary from outer boundary. A. Outer boundary. B. Extended boundary conditions. C. Extended boundary has same size and shape as original object boundary. A more sophisticated approach is based on detecting common boundary segments between adjacent regions and vertex points in boundary segment connections. The detection process is based on a lookup table which defines all 12 possible situations of the local configuration of 2x2 pixel windows, depending on the previously detected direction of boundary and on the status of window pixels which can be inside or outside a region. Extended boundary tracing. Algorithm. Define a starting pixel of an extended boundary in a standard way. The first region pixel is found in a left to right and top to bottom line by line. The first move along the boundary traced from the starting pixel in the direction dir equals 6 down, corresponding to the situation as shown in the figure. Trace the extended boundary using the lookup table until a closed extended border results. Note that there is no whole border tracing included in the algorithm. The holes are considered separate regions and therefore the borders between the region and its hole are traced as a border of the hole. Lookup table defining all 12 possible situations that can appear during extended border tracing. Current position is in the central pixel. The direction of the next move depends on the local configuration of background and region points and on the direction of approach to the current pixel. The lookup table approach makes the tracing more efficient than conventional methods and makes parallel implementation possible. In addition to extended boundary tracing, it provides a description of each boundary segment in chain code form together with information about vertices. This method is very suitable for representing borders in higher-level segmentation approaches, including methods that integrate edge-based and region-based segmentation results. Moreover, in the conventional approaches, each border between two regions must be traced twice. The algorithm can trace each boundary segment only once, storing the information about what has already been done in double-linked lists. A more difficult situation is encountered if the borders are traced in gray-level images, where regions have not yet been defined. The border is represented by a simple path of high-gradient pixels in the image. Border tracing should be started in a pixel with a high probability of being a border element, and then border construction is based on the idea of adding the next elements which are in the most probable direction. To find the following border elements, edge gradient magnitudes and direction are usually computed in pixels of probable border continuation. Border detection as graph searching. Whenever additional knowledge is available for boundary detection, it should be used. For example, known approximate starting point and ending point of the border. Even some relatively weak additional requirements such as smoothness, low curvature, etc. may be included as prior knowledge. A graph is a general structure consisting of a set of nodes Ni and arcs between the nodes Ni and J. We consider oriented and numerically weighted arcs, these weights being called costs. The border detection process is transformed into a search for the optimal path in the weighted graph. Assume that both edge magnitude and edge direction information is available in an edge image. The figure depicts graph representation of edge direction and corresponding graph. To use graph search for region border detection, a method of oriented weighted graph expansion must first be defined. Boundary detection as dynamic programming. It is an optimization method based on the principle of optimality. It is search for optima of functions in which not all variables are simultaneously interrelated. The representations in the figure show edge following as dynamic programming. The main idea of the principle of optimality is, whatever the path to the node E was, there exists an optimal path between E and the endpoint. In other words, if the optimal path start point and end point goes through E, then both its paths are also optimal. The figure shows the dynamic programming A. One step of the cost calculation, B. Graph layers, node notation. If the graph has more layers, the process is repeated until one of the endpoints is reached. The complete graph must be constructed to apply dynamic programming, and this may follow general rules given in the previous section. The objective function must be separable and monotonic, as for the A algorithm. Evaluation functions presented in the previous section may also be appropriate for dynamic programming. Algorithm for boundary detection as dynamic programming. Specify initial cost Cxi of all nodes in the first graph layer, where I equals 1 to n, and partial path cost g to the power of m of I, k, m equals 1 to m minus 1. Repeat step 3 for all m equals 1 to m minus 1. Repeat step 4 for all nodes k equals 1 to n in the graph layer m. The following cost equation results. Find an optimal node xk to the power of m star in the last graph layer m and obtain an optimal path by backtracking through the pointers from xk raised to the power of m star to xi star. Edge linking and boundary detection using Hough Transform. The Hough Transform is a technique which can be used to isolate features of a particular shape within an image. Hough Transform is most commonly used for detection of regular curves such as lines, circles, ellipses, etc. The main advantage of the Hough Transform technique is that it is tolerant of gaps in feature boundary descriptions and is relatively unaffected by image noise. It maps straight line y equals mx plus c in a Cartesian coordinate system into a single point in the rho, theta plane, or x cos theta plus y sin theta. For a point x, y in the Cartesian coordinate plane, there will be an infinite number of curves in the rho, theta plane. When 2 points xi, yi and xj, yj lie on the same straight line, the curves in the rho theta plane, which correspond respectively to the 2 points xi, yi and xj, yj in the Cartesian plane, will intersect at a point. This intersection point determines the parameter of the line that joins these 2 points. Similar arguments apply for the 3 collinear points. This property between Cartesian plane and the parametric plane will be useful in finding the line that fits points in the xy plane. The Hough Transform approach is to find the points of intersection in the curves, each of which corresponds to a line in the Cartesian xy plane. The figure shows the expected ranges of rho and theta. The two-dimensional parameter space is described into the finite interval, accumulator cell, or 2D bins. Each of the cells is first initialized to 0. For each point in the Cartesian image plane, compute the value of rho I for various values of theta I. In the equation, rho I equals x cos theta I plus y sin theta I. If there are n collinear points lying in a line, we get n sinusoidal curves that intersect at rho I theta I in the parametric space. The peaks in the rho theta plane accumulator array, therefore, give strong evidence of the existence of lines in the image. The Hough transforms can be generalized to detect circles as described by x minus a whole squared plus y minus a whole squared equals r squared. Now we get 3 parameters a, b, and r as parameters of a circle. This results in a 3-dimensional accumulator array where each accumulator bin is indexed by a discrete value of a, b, r. The figures show the illustration of the Hough transform. In the figures above, A represents infrared images, B threshold gradient images, C Hough transform, and D linked pixels. Edge detection and its performance. Edge detection. Edges are significant local changes of intensity in an image. Edges typically occur on the boundary between 2 different regions in an image. Goal of edge detection. Produce a line drawing of a scene from an image of that scene. Important features can be extracted from the edges of an image. For example, corners, lines, curves. These features are used by higher-level computer vision algorithms. For example, recognition. What causes intensity changes? Various physical events cause intensity changes. Geometric events. Object boundary, that is, discontinuity in depth and/or surface color and texture. Surface boundary, discontinuity in surface orientation and/or surface color and texture. Non-geometric events, specularity, direct reflection of light such as a mirror, shadows from other objects or from the same object. Interreflections. Edge descriptors, edge normal. Unit vector in the direction of maximum intensity change. Edge direction. Unit vector is perpendicular to the edge normal. Edge position or center. The image position at which the edge is located. Edge strength related to the local image contrast along the normal. 4 steps of edge detection. Smoothing. Suppress as much noise as possible without destroying the true edges. Enhancement. Apply a filter to enhance the quality of the edges in the image. Sharpening. Detection. Determine which edge pixel should be discarded as noise and which should be retained. Usually, thresholding provides the criterion used for detection. Localization. Determine the exact location of an edge. Sub-pixel resolution might be required for some applications, that is, estimate the location of an edge better than spacing between pixels. Edge thinning and linking are usually required in this step. Edge detection using derivatives. Calculus describes changes of continuous functions using derivatives. An image is a 2D function, so operators describing edges are expressed using partial derivatives. Points which lie on an edge can be detected by detecting local maxima or minima of the first derivative, detecting the zero crossing of the second derivative, differentiating 1D signals. To compute the derivative of a signal, we approximate the derivative by finite differences. Computing the first derivative. The equation is seen on the screen. We will now see some examples using the edge models and the mask -1, 0, 1. Computing the second derivative. The equation is seen on the screen. This approximation is centered about x plus 1. By replacing x plus 1 by x, we obtain a different set of equations. We will now see an example using the edge models. Edge detection using gradient. Definition. The gradient is a vector which has certain magnitude and direction. Del f equals dou f by dou x, dou f divided by dou y. The equations for magnitude and direction of del f can now be seen. To save computations, the magnitude of gradient is usually approximated by properties of the gradient. The magnitude of gradient provides information about the strength of the edge. The direction of gradient is always perpendicular to the direction of the edge. The edge direction is rotated with respect to the gradient direction by -90 degrees. Equations for estimating the gradient with finite differences can now be seen. The gradient can be approximated by finite differences. Using pixel coordinate notation, remember j corresponds to the x direction and I to the negative y direction. Example. Suppose we want to approximate the gradient magnitude at z5. The magnitude is given by the equation shown. We can implement dou I, dou X, and dou I, dou Y by using the following masks: -1, 1, 1, -1. The equations for the robot's edge detector can now be seen on the screen. The approximation can implement by using the following masks. Note, mx and my are the approximation at I plus 1 by 2, j plus 1 by 2. This is followed by the Prewitt edge detector. Consider the arrangement of pixels about the pixel I, j. The partial derivatives can be computed by the constant C implies the emphasis given to pixels closer to the center of the mask. Setting C equals 1, we get the Prewitt operator mx and my. The Sobel edge detector. Setting C equals 2, we get the Sobel operator as follows. Main steps in edge detection using masks. 1. Smooth the input image. F cap of x, y equals f of x, y star g of x, y. 2. F cap of x equals f cap x, y star mx of x, y. 3. F cap y equals f cap x, y star my of x, y. 4. Magnitude x, y equals mod of f cap x plus mod of f cap y. Step 5. Direction of x, y equals tan to the power of -1 of f cap y by f cap x. If magnitude x, y greater than t, then the possible edge point can be computed as shown on the screen. A comparison of various edge detectors without filtering can now be seen. Isotropic property of gradient magnitude. The magnitude of gradient is an isotropical operator. Some practical issues. The differential masks act as high-pass filters which tend to amplify noise. To reduce the effects of noise, the image needs to be smoothed first with a low-pass filter. The noise suppression localization trade-off. A larger filter reduces noise but worsens localization. That is, it adds uncertainty to the location of the edge, and vice versa. How should we choose the threshold? Edge thinning and linking are required to obtain good contours. Criteria for optimal edge detection. 1. Good detection. The optimal detector must minimize the probability of false positives, detecting spurious edges caused by noise, as well as that of false negatives, missing real edges. 2. Good localization. The edges detected must be as close as possible to the true edges. 3. Single response constraint. The detector must return one point only for each true edge point, that is, minimize the number of local maxima around the true edge created by noise. The canny edge detector. This is probably the most widely used edge detector in computer vision. Canny has shown that the first derivative of the Gaussian closely approximates the operator that optimizes the product of signal-to-noise ratio and localization. The analysis is based on step edges corrupted by additive Gaussian noise. The algorithm for computing fx and fy can now be seen. As well as computing the gradient magnitude can now be seen. Apply non-maxima suppression. Apply hysteresis thresholding and edge linking. Non-maxima suppression. To find the edge points, we need to find the local maxima of the gradient magnitude. Broad ridges must be thinned so that only the magnitudes at the points of greatest local change remain. All values along the direction of the gradient that are not peak values of a ridge are suppressed. The algorithm for each pixel x, y can now be seen. Hysteresis thresholding and edge linking. The output of non-maxima suppression still contains local maxima created by noise. Can we get rid of them just by using a single threshold? If we set a low threshold, some noisy maxima will be accepted too. If we set a high threshold, true maxima might be missed. The value of true maxima will fluctuate above and below the threshold, fragmenting the edge. A more effective scheme is to use two thresholds. A low threshold, TL, a high threshold, TH. Usually, TH is approximately equal to 2 TL. It involves the following steps. 1. Produce two threshold images I1 as seen. Link the edges in I2 into contours. Look in I1 when a gap is found. By examining the 8 neighbors in I1, gather edge points from I1 until the gap has been bridged to an edge in I2. The algorithm performs edge linking as a byproduct of double thresholding. Edge detection using second derivative. Edge points can be detected by finding the zero crossings of the second derivative. There are two operators in 2D that correspond to the second derivative: Laplacian, second directional derivative. The Laplacian equations are now seen, followed by an example. The Laplacian can be implemented using the mask shown below. Example. Properties of the Laplacian. It is an isotropic operator. It is cheaper to implement one mask only. It does not provide information about edge direction. It is more sensitive to noise. Differentiates twice. The Laplacian of Gaussian, LOG. To reduce the noise effect, the image is first smoothed with a low-pass filter. In the case of the LOG, the low-pass filter is chosen to be a Gaussian. Sigma determines the degree of smoothing. Mask size increases with sigma. The Laplacian of Gaussian equations can be shown to follow as below. Gradient versus LOG. Gradient works well when the image contains sharp intensity transitions and low noise. Zero crossings of LOG offer better localization, especially when the edges are not very sharp. The second directional derivative. This is the second derivative computed in the direction of the gradient. Multi-scale processing. Scale space. A serious practical problem with any edge detector is a matter of choosing the scale of smoothing, that is, the value of sigma using a Gaussian. For many applications, it is desirable to be able to process an image at multiple scales, determine which edges are most significant in terms of the range of scales over which they are observed to occur. Conclusion. In this chapter, we have covered the following in detail: edge detection, boundary detection, edge detection performance, boundary detection performance.